Welcome to our series of short educational videos about important concepts of building performance. This video discusses conditions under which adding renewable energy generation to the power grid could cause higher utility energy costs for the customer base. We have two different electric energy supplies. Let's look at them. On the left side is the conventional way we are used to receive our electricity supply. Here, a central power plant produces enough electricity to supply the grid demand at any time, as is required. This type of energy supply is also referred to as dispatchable supply. The power plant is standing by to dispatch or supply power whenever it is called for. This means there is enough standby power available to meet the highest practically probable demand at any time of the day or year. And usually some references are also built in to account for generation capacity to go offline. On the right side is the intermittent power supply provided by renewables. The power supply is intermittent since solar and wind power generation depends on availability of sun and wind from the environment. There are of course other and also important sources of renewables which are not intermittent but can be regarded as dispatchable, such as biofuel, hydroelectric or geothermal power generation. But at this time we consider only the intermittent power from solar and wind because they have so much potential. This graph illustrates a simplified daily distribution of conventional grid power supply. The grid supply is dispatchable power where the power supplied matches the power demand. Remember, we cannot store electricity and electricity must be immediately consumed when it is generated. The curve shows a simplified yet commonly seen daily pattern of power supply and demand. The supply and demand can look different depending on the grid and the location we are looking at, but it always follows a similar pattern. It is never flat, it is never uniform in terms of electricity generated and used. We can see in our illustration that there is a large increase in power supply during the middle of the day. There is a maximum demand, which we represent the peak power demand. In this slide, we define two important factors that affect the financial performance of the grid power supply system. The first factor is the amount of electric energy that the utility can sell. This is represented with a gray area under the curve. Since the electric energy, as kilowatt hours, is the product of power, which is kilowatt, and time, here hours, the energy that can be sold is the gray area under the curve. The second factor is the peak power that has to be satisfied at any time. Enough power generating capacity must be kept available to satisfy the peak. The higher the peak, the larger is the required supply capacity. Since the cost of power plant increases with size, having a high peak can be very costly for the utility. Let's now look at intermittent and solar energy and how it compares. This slide shows us a typical daily distribution of solar power generation. Solar power is generated only during a part of the day and after small generation rates in the morning and evening hours. Power generation are usually at the maximum during the midday hours, as we can see here, during about 11 to 2, something like that. Notice that the solar energy is an intermittent and is not dispatchable power. The supply does not follow the demand, and the generation capacity is dictated by the environmental condition. And this one is beyond the control of the operator, of course. So what we see here is we are not following a certain demand, but basically whatever is available we put in, whatever is available from the sun. In this figure, a realistic case of significant renewable power supply to the grid is shown. And this actually occurs during the midday hours, and this is consistent with what we've seen before. The energy provided by renewables is highlighted here by the yellow area. Since the dispatchable power is replaced by intermittent power, the energy derived from dispatchable power is reduced, and therefore the size of the gray area decreases, and so does the amount of energy that can be sold by the utility. What has not changed is the typical peak power for which dispatchable power generation capacity has to held available, regardless whether the renewables provide power or not. In the event of no efficient sunshine and no wind, these renewables do not provide the energy that is presented by the yellow area in our figure. And here's our conclusion. When more renewables are providing intermittent power, while that peak power has still to be satisfied at any time, the cost per kilowatt hour of energy must increase, since less kilowatt hours are sold to pay for the same fixed cost payments. Let's see what is behind this argument. And this slide shows us two types of cost that we must pay to the utility. The first cost type represents fuel-related energy cost, which pay for the quantities of fuel that is required to generate electricity. It is obviously the more power is consumed, the higher are the fuel-related costs, because the more energy we use, the more energy which is supplied by the fuel. The second cost type represents fixed cost, and they are required to pay for the capital cost of power plant and infrastructure and other non-fuel related operational and management costs. This also includes the cost for personnel. These costs must be paid by the utility regardless how much electricity is generated in that particular moment or over time, even if the power plant sits idle. Let's think out of the box for right now. And we're actually thinking about the different scenarios to make the same argument, but in a different industry. Here we're looking at a trucking company. This company must invest into trucks, and the trucks must operate to generate revenues. The company must make a projection to buy enough trucks to serve the clients. So they have to anticipate their capacity to meet demands. Because you do not really want to lose customers by saying, hey, we don't have enough trucks. We kept it safe. If for any reason now the trucks are sitting idle for a significant time, the finances of that company is most likely stretched. Loan costs for the trucks, office expenses and salaries must be paid even if the trucks do not operate and create revenues. So I think after going through our discussion, we appreciate that the financial management and operation of an electric grid with a significant portion of intermittent power from renewables is not a trivial matter. I think it is really complicated. The portion of grid supply that is provided by renewables will increase in the future, there's no doubt. And it is paramount that energy costs are still be affordable for all types of customers, regardless if they have their own renewable power supply or not. And in order to mitigate financial and operational problems, effective technologies and solutions must be developed and used. The following are some candidate solutions. Significant energy efficiency at customer. Using less energy also reduces the peak load. Different cost structure for power during peak demand hours. This is actually a proven way to reduce the peak demand. In some regions in the world, very high demand charges are levied on customers with large loads during the typical peak demand hours of the day. If, on the other hand, the customer agrees that his or her demand is automatically managed by the utilities, these high energy charges are waived. This is a very effective incentive. Smart grids to manage the grid loads. This entails new technologies of managing the demand as well as the supply in a new type of grid. Smart appliances to control the demand. These appliances are still something new. Imagine you have a smart dryer, and since you are in a program that for automatic demand control, you may pay much less for energy. So you don't incur high demand charges. So imagine you want to start your smart dryer, and here's a thing could happen. You press that start button, but you do not notice that the dryer starts to operate. Instead, in the background, which you don't see, a request is sent to the power company to reserve a slot when the demand can be dispatched. So after a while of waiting, the smart dryer will start, and the customer can save a lot of money. I think this is a fabulous technology. Battery storage for renewables to reduce the peak demand on the grid. Storing the solar energy in batteries instead of feeding it to the grid can be cost effective and help to manage the grid. Use of thermal storage for thermal energy services such as air conditioning and hot water and dehumidification. Storage of heat energy instead of electric heat can be very effective and much less costly if all we need is heat and not electric energy. Imagine one of the most wasteful way to use electricity and energy is to heat water with electricity. It is convenient, of course, but a lot of waste and a lot of energy losses are there. Behavioral changes of using energy. Finally, changes in our behavior about how to use energy can perhaps make the largest positive impact. Openness to see the use of electricity and energy in a resource-responsible way can make it possible to use new and innovative technologies and give us patience, even if not all of our immediate energy needs are fulfilled to the fullest. And others. There might be other technology and solution coming out in the future. We need to be open for changes. I think a lot of interesting new technologies will be coming towards us, and I think we should be grateful and open to that. This concludes our discussion. We now come to our assessment. Let's see how much you remember from our discussion. The self-assessment is an important step in the learning process. You can either contemplate and answer the question yourself, or you can discuss the question with friends and colleagues. It is a very proven way that the best way to learn a topic is to explain it to somebody else, because you really have to know it. And then comes answers and the question, and you have to give a good answer. You see several self-learning assessment questions below. Please try to answer them. You might want to review portions of this video. Thanks for trying. What is the difference between dispatchable and intermittent power supply? What happens to the power plant electricity generation operation when significant quantities of intermittent power is provided by renewables? How do you like the comparison to the trucking company? And what are the similarities to supply of electricity? What are some of the solutions with which we can solve some of the challenges as we add more and more intermittent power from renewables to our grid? This concludes our video. Thank you for your interest, and like always, please join us again for one of our other videos about important concepts of building performance.